Hey guys, welcome to your first actual lesson of the flipped classroom in Honors Algebra 2. I did end up posting the lesson that I recorded of solving linear systems graphically. Okay, so check that out. Make sure you know how to solve linear systems graphically. Make sure you know what the three types of solutions for a linear system are. Okay. So now, today we're going to talk about solving systems algebraically. And there's two ways that we're going to solve systems algebraically. So we're going to add to the ways that you know how to solve a system two things today: substitution and elimination of linear combination. I'm going to use the word elimination. Your book uses the phrase linear combination, so that might be on a couple of the worksheets that you guys are going to work on. So by the end of today, you should be able to solve systems of linear equations using substitution and linear combination. And again, stop the video, pause, work at your own pace. If you're familiar with this stuff, kind of skip ahead, go through the examples real quick. Okay. This is the same application problem that we had in class today, so we're not going to identify all our key stuff again. We know there's going to be an equation for Trevor, an equation for Joe. Trevor's knocking down 4 every minute. Joe's knocking down, he already knocked down 6. He's knocking down 2 every minute. So now last time, we graphed these, we saw where they intersected, we interpreted what that intersection point meant in terms of an x, y ordered pair. Today, we're going to use what we call substitution. So here, y is the same thing as 4n. So we can substitute in 4n for our second equation where we see y. Okay? So now we can solve for n. We can go through, solve this equation for n, subtract 2n on both sides. We're going to have 2n equals 6. Divide by 2 on both sides, and n would be 3. Okay, so ask yourself, what did n stand for? N stood for the number of minutes. So at 3 minutes, they've made the same number of 3's. So now with that number, to find our other variable, to find what y is going to be, you can substitute it in for either of the equations up here. So for the top equation, it'd be 4 times 3, which would be 12. For the bottom equation, it'd be 4 times 2. Sorry, for 6 plus 2 times 3, which is going to be 6 plus 6, which is also going to be 12. So how many 3's have they made at 3 minutes? They've made 12 3's. Okay? So that's kind of the rationale of substitution. That's what we're doing when we're working on substitution. And there are more or less 6 steps to substitution. Okay? You don't have to memorize all these steps. Just know what we're trying to do when we substitute. Step 1, we're going to solve for a variable. In this PowerPoint said solve for y. In this example, we're going to solve for y, but it could be either variable. It doesn't matter. Okay, so you're looking up here. You're asking yourself, which variable is going to be the easiest to solve for? Okay, up here, the y's, they don't have coefficients, so they're going to be the easiest ones to solve for. You could solve for y in either equation up here. It doesn't matter. I'm going to solve for y in the second equation just so I don't have to deal with some negatives. So I'm going to add 3x to both sides, and y is going to equal 3x minus 5. Okay? So I solve for a variable. There's step 1. Easy as that. Substitute it in for the second equation. So what that means is we're going to substitute what y is into the second equation. Okay, so that second equation is going to be 8x plus whatever y is equals negative 16. So now we know y is the same thing as 3x minus 5. So we can substitute 3x minus 5 in for y in that other equation. Okay, the reason that we're trying to do that is there are only x's in our equation now, so we can solve for x. We can find out what x is going to be. So there's our third step. So we solve for a variable in step 1. Now we're solving for the other variable. We're giving the other variable a numerical value so that we can solve the system. Okay. So combine my terms, 8x plus 3x, we're going to have 11x's. Minus 5 equals negative 16. Add 5 on both sides, and we'll have 11x equals negative 11. Divide by 11 on both sides, and x is going to be negative 1. Alright, so we just solved for the other variable. Substitute back into your system and solve for the first variable. And this PowerPoint just kind of uses x and y's interchangeably. I'm putting it in a more general form just so you guys know that you can use x or y for your first step, and then you can go from there. So we're going to substitute x equals -1 back in to either of our equations at the top there. I'll just pick the top equation, it doesn't matter either way. So 8 times -1 plus y equals -16. So 8 times -1 is -8, plus y equals -16. Add 8 on both sides, and y is going to equal -8. Okay? So we know what x is, we know what y is. How do we always write our answer for a system of linear equations? We're going to write the answer as ordered pair. Remember, when we're graphing these, they meet at a point. That point is what makes both of those equations true. Okay? So we'll write our answer as an ordered pair. It's a place on the graph, so we're going to write it like a place on the graph. And then step 6 is check our answer. Remember, when we're checking our answer, we're going to plug it back into our system. The solution of the system is when they both are going to be true. Okay? So here, we need to see if the point -1, -8 makes both of our equations true. Alright, so let's check it out. Equation 1, 8 times -1 plus a -8 equals -16. 8 times -1 is -8 plus a -8 equals -16. So I start with -8. I'm adding a negative number, so I'm getting more negative. So 8 plus -8 would be -16. Alright, and then equation 2. Was -3x plus y equals -5. Okay, so substitute our point in. -3 times -1 plus -8 equals -5. -3 times -1 is going to be 3, plus a -8 equals -5. That's a true thing. So our solution worked in both of our equations, so our solution is good. Okay, it's a good solution to that system. Alright, let's look at one more example of substitution. Okay, step 1, solve for a variable. Go up here, see which variable is going to be the easiest to solve for. It's going to be the variable that doesn't have any coefficients. So the x in this top equation doesn't have any coefficients. So we add 3y to both sides in equation 1. So now equation 1 is x equals 3y plus 4. Okay? So step 2, substitute that into the second equation. Okay? So equation 2, we know what x is. X is the same thing as 3y plus 4, so we can substitute that in for x in our second equation. Okay? Make sure we have those parentheses, because now what we need to do, we're going to solve for y, solve for that other variable. So now we're going to have to distribute. Okay? 3 times 3y is going to be 9y. 3 times 4 is going to be 12. So 9y plus 12 minus 3y equals 24. Combine my terms, 9y minus 3y is going to be 6y. So 6y plus 12 equals 24. What can we add or subtract to get y by itself? We'd subtract 12 on both sides. So 6y is going to be 12. Divide by 6 on both sides, and y is going to be 2. Okay? So we solve for that variable. Now, we're going to substitute that variable back in so we can solve for our other variable. I'm going to substitute it in for that first equation at the top there. So x minus 3 times 2 equals 4. X minus 6 equals 4. Add 6 to both sides, x is going to be 10. Okay? Step 5, I believe it was, write your answer as an ordered pair. pair is going to be 10, 2. And that's our final answer. I just circled a couple steps to get to that final answer. Write your x and your y's in order pair. And now our last step, step 6. Step 6 is substitute it back in, make sure it's okay. So for equation 1, x is negative 10 minus 3 times y, which is 2, equals 4. So 10 minus 6 equals 4. That's a true thing, so we're good there. Let's look at equation 2. 3 times 10 minus 3 times 2 equals 24. 3 times 10 is 30. Minus 3 times 2 is 6. 30 minus 6 would be 24. Okay, so our answer, 10, 2, is a good answer and makes both of those equations true in our system. Remember, that's what we're looking for. A solution to a system makes both of those equations true. When we're graphing it, it was the point that both of the equations had in common. It was the only point that was on both of those equations. Now, when we're using substitution or elimination here, it's